Welcome to CO556 Network Systems. This is week 11 and we're covering Cisco Chapter 14 Routing Concepts this week. The objective for this week is to explain how routers use information in packets to make forwarding decisions. It will explain how routers determine the best path, how routers forward packets to the destination. We'll configure basic settings on a router, describe the structure of a routing table, and compare static and dynamic routing concepts. Path determination. Two functions of a router. When a router receives an IP packet on an interface, it determines which interface to use to forward the packet to its destination. This is known as routing. The interface that the router uses to forward the packet may be the final destination, or it may be a network connected to another router that is used to reach the destination network. Each network that a router connects to typically requires a separate interface, but this may not always be the case. The primary functions of a router are to determine the best path to forward packets based on the information in its routing table, and to forward packets towards their destination. Router functions example. The router shown here uses its IP routing table to determine which path, or route, to use to forward a packet. In the diagram, R1 and R2 will use their respective IP routing tables to first determine the best path, and then forward the packet. We can see here in the example a routing table for R1. So show IP route is the command to show the routing table, and a particular route has been highlighted. So it's a static route, it has an S at the end of it, and it's from 192.168.3 network. And to reach that network, we're going via 192.168.2.2 interface. So routers use the routing table like a map to discover the best path for a given network. Best path equals longest match. The best path in the routing table is also known as the longest match. The routing table contains route entries consisting of a prefix, is the network address, and prefix length. For there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far left bits must match between the IP address of the packet and the route in the routing table. The prefix length of the route in the routing table is used to determine the minimum number of far left bits that must match. The longest match is the route in the routing table that has the greatest number of far left matching bits with the destination IP address of the packet. The longest match is always the preferred route. Note, the term prefix length will be used to refer to the network portion of both IP version 4 and IP version 6 addresses. IP version 4 longest match example. In the table below, an IPv4 packet has the destination IPv4 address of 172.16.0.10. The router has 3 route entries in its IPv4 routing table that match this packet. 172.16.0.0/12, 172.16.0.0/18, and 172.16.0.0/26. Of the 3 routes, 172.16.0.0/26 has the longest match and would be chosen to forward the packet. For any of these routes to be considered a match, there must be at least the number of matching bits indicated by the subnet mask of the route. IPv6 longest match example. An IPv6 packet has the destination IPv6 address of 2001 DB8 C00099. This example shows 3 route entries, but only 2 of them are a valid match, with one of those being the longest match. The first 2 route entries have prefix lengths that are required number of matching bits as indicated by the prefix length. The third route entry is not a match because its /64 prefix requires 64 matching bits. Build the routing table. Directly connected networks. Added to the routing table when a local interface is configured with an IP address and subnet mask, prefix length, and is active, i.e. up and up. Remote networks. These are networks that are not directly connected to the router. Routers learn about remote networks in two ways, either via static routes, which are added to the routing table when a route is manually configured, or dynamic routing protocols, which are added to the routing table when the routing protocols dynamically learn about the remote network. Default route specifies a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. The default route can be entered manually as a static route or learned automatically from dynamic routing protocol. A default route has a 0 prefix length. This means that no bits need to match the destination IP address for its route entry to be used. If there are no routes which match longer than 0 bits, the default route is used to forward the packet. The default route is sometimes referred to as a gateway of last resort. Packet forwarding. Packet forwarding decision process. 1. The data link frame with an encapsulated IP packet arrives on the ingress interface. Step 2. The router examines the destination IP address in the packet header and consults its IP routing table. Step 3. The router finds the longest matching prefix in the routing table. Step 4. The router encapsulates the packet in a data link frame and forwards it out of the egress interface. The destination could be a device connected to the network or the next hop router. However, if there is no matching route entry, the packet is then dropped. After a router has determined the best path, it could do the following. Forward the packet to a device on a directly connected network. If the route entry indicates that the egress interface is a directly connected network, the packet can forward directly to the destination device. Typically, this is an Ethernet LAN. To encapsulate the packet in the Ethernet frame, the router needs to determine the destination MAC address associated with the destination IP address of the packet. The process varies based on whether the packet is an IP version 4 or IP version 6 packet. After a router has determined the best path, it could also forward the packet to a next hop router. If the route entry indicates that the destination IP address is on the remote network, meaning a device on a network is not directly connected, the packet must be forwarded to the next hop router. The next hop address is indicated in the route entry. If the forwarding router and the next hop router on an Ethernet network, a similar process, IRP and ICMPv6 neighbor discovery, will occur for determining the destination MAC address of the packet as described previously. The difference is that the router will search for an IP address of the next hop router in its ARP table or neighbor cache, instead of the destination IP address of the packet. Note, this process will vary for other types of layer 2 networks. After a route has been determined, it could also drop the packet. No match in the routing table. If there is no match between the destination IP address and the prefix in the routing table, and if there is no default route, the packet will be dropped. End-to-end packet forwarding. The primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. For example, the data link frame format of a serial link could be point-to-point, PPP protocol. High-level data link control, HDLC protocol, or some other layer 2 protocol. Packet forwarding mechanisms. The primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. The more efficiently a router can perform this task, the faster packets can be forwarded by the router. Routers support the following three packet forwarding mechanisms: process switching, fast switching, and Cisco Express Forwarding, CEF. Process switching. This is an older packet forwarding mechanism still available for Cisco routers. When a packet arrives on an interface, it is forwarded to the control plane, where the CPU matches the destination address with an entry in its routing table, and then determines the exit interface and forwards the packet. It is important to understand that the router does this for every single packet, even if the destination is the same for a stream of packets. In fast switching, which is another older packet forwarding mechanism, which was the successor to process switching, fast switching uses a fast switching cache to store next hop information. When a packet arrives on an interface, it is forwarded to the control plane, where the CPU searches for a match in the fast switching cache. If it is not there, it is process switched and forwarded to the next exit interface. The flow of information for the packet is then stored in the fast switching cache. If another packet going to the same destination arrives on the interface, the next hop information in the cache is reused without the CPU intervention. Cisco Express Forwarding is the most recent and default Cisco iOS packet forwarding mechanism. Cisco Express Forwarding builds a forwarding information base and an adjacency table. Table entries are not packet triggered like fast switching, but change triggered, such as when something changes in the network topology. When a network has converged, the forwarding information base and adjacency tables contain all the information that a router would have to consider when forwarding a packet. Basic router configuration review. Topology. The topology in this figure will be used for configuration and verification examples. It will also be used in the next topic to discuss the IP routing table. Configuration commands. Here we see some of the configuration commands that have been applied to this example. We see the enable command, configure terminal, hostname being set to R1, enable secret class, the enable password being put on as a class, line console passwords and logging, VTYs being set up, service password encryption, banner messages being added, message of the day, and then we have some examples for IPv6. So IPv6 unicast routing has been initiated, and the interfaces are being set up. Gigabit Ethernet 000. Description, IP address for IP version 4, an IP address for version 6, and also a linked local address for IP version 6 on each interface. And then the copying running config to startup config in order to save the settings. And verification commands. So these are common verification commands, include the following. So show IP interface brief to look at the interfaces that have been set up on a router. Show running config interface to look at specifically the interface setup within the running configuration file. Show interfaces to show a full breakdown of all the interfaces on the device. Show IP interface to look specifically at the logical IP addressing within the interfaces. Show IP route to look at the routing table, and obviously ping in order to test end-to-end connectivity. For IP version 6, as it says, you can just simply replace IP with IPv6, and that will give you the version of the command for IP version 6. Filtering command output. Filtering commands can be used to display specific sections of output. To enable the filtering command, enter a pipe, like a straight line bar character. After the show command, and then enter a filtering parameter and a filtering expression. The filtering parameters that can be configured after the pipe include section, which displays the entire section that starts with the filtering expression. Include, this includes all output lines that match the filtering expression. Exclude, this excludes all output lines that match the filtering expression. Begin, this displays all the output lines from a certain point, starting with the line that matches the filtering expression. Note, output filters can be used in combination with any show command. We have a little packet tracer exercise this week called Basic Router Configuration Review. And in that packet tracer, you get to configure devices and verify connectivity and display router information. The IP routing table. Route sources. A routing table contains a list of routes to known networks, prefixes and prefix lengths. The source of this information is derived from the following: directly connected networks, static routes, and dynamic routing protocols. The source of each route in the routing table is identified by a code. Common codes include the following: L, which identifies the address assigned to a router interface; C, which identifies a directly connected network; S, which identifies a static route created to a specific or to reach a specific network; O, identifies a dynamically learned network from another router using the OSPF routing protocol. The asterisk, this route is a candidate for a default route. Routing table principles. There are 3 routing table principles as described in this table below. These are issues that are addressed by the proper configuration of dynamic routing protocols or static routes on all the routers between the source and destination devices. First principle is every router makes its decision alone based on the information it has in its own routing table. So in our example, R1 can only forward packets using its own routing table, and R1 does not know what routes are in the routing tables of the other routers, e.g. R2. Principle 2 is the information in the routing table of one router does not necessarily match the routing table of another router. Just because R1 has a route in its routing table to a network in the internet via R2, that does not mean that R2 knows about the same network. Principle 3 is that routing information about a path does not provide return routing information. R1 receives a packet with a destination IP address of PC1 and the source IP address of PC3. Just because R1 knows to forward the packet out of its gigabit Ethernet 000 interface doesn't necessarily mean that it knows how to forward packets originating from PC1 back to the remote network of PC3. Routing table entries. In the figure shown here, the numbers identify the following information. 1. The route source. This identifies how the route was learned. 2. Destination network, prefix and length. This identifies the address of the remote network. 3. Administrative distance. This identifies the trustworthiness of the route source. Lower values indicate preferred static route or route source. Metric. 4. This identifies the value assigned to reach the remote network. Lower values indicate preferred routes. 5. Next hop. This identifies the IP address of the next router to which the packet would be forwarded. 6. Route timestamp. This identifies how much time has passed since the route was learned. 7. The exit interface. This identifies the egress interface to use for outgoing packets to reach their final destination. Note, the prefix length of the destination network specifies the minimum number of far left bits that must match between the IP address of the packet and the destination network prefix for this route to be used. Directly connected networks. To learn about any remote networks, the router must have at least one active interface configured with an IP address and subnet mask prefix length. This is known as a directly connected network or directly connected route. Routers add a directly connected route to its routing table when an interface is configured with an IP address and is activated. A directly connected network is denoted by the status code of C in the routing table. The route contains a network prefix and prefix length. The routing table also contains a local route for each of its directly connected networks, indicated by the status code of L. For IPv4 local routes, the prefix length is /32, and for IPv6 local routes, the prefix length is /128. This means the destination IP address of the packet must match all the bits in the local entry, in the local route, for this route to be a match. The purpose of the local route is to efficiently determine when it receives a packet for the interface instead of a packet that needs to be forwarded. Static routes. After directly connected interfaces are configured and added to the routing table, static or dynamic routing can be implemented for accessing remote networks. Static routes are manually configured. They define an explicit path between two networking devices. They are not automatically updated and must be manually reconfigured if the network topology changes. Static routing has three primary uses. It provides ease of routing table maintenance in smaller networks that are not expected to grow significantly. It uses a single default route to represent a path to any network that does not have a more specific match with another route in the routing table. Default routes are used to send traffic to any destination beyond the next upstream router. It routes to and from stub networks. A stub network is a network accessed by a single route and the router has only one neighbor. Static routes in the IP routing table. The topology in the figure below is simplified to show only one LAN attached to each router. The figure shows IPv4 and IPv6 static routes configured on R1 to reach 10.0.4.0/24 network and 2001 DB8 ACAD 4/64 networks on R2. Dynamic routing protocols. Dynamic routing protocols are used by routers to automatically share information about the reachability and status of remote networks. Dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. In the diagram here, you can see that R1 says, I will share with R2 all the networks I know about and tell R2 when there are any changes. Similarly, R2 says, I will share with R1 all the networks I know about and tell R1 when there are any changes. So in dynamic routing protocols, we're sharing routing information between routers. Dynamic routes in the routing table. OSPF, which is Open Shortest Path First, is now being used in our sample topology to dynamically learn all the networks connected to R1 and R2. The routing table entries use the status code of O to indicate the route was learned by the OSPF routing protocol. Both entries also include the IP address of the next hop router via IP address. Note IP version 6 routing protocols use the link local address of the next hop router. Also note that OSPF routing configuration for IP version 4 and IPv6 is not something that we're going to specifically cover in the module. The default route. The default route specifies a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. The default route can be either a static route or learned automatically from a dynamic routing protocol. A default route has an IPv4 route entry of 0.0.0.0/0 or an IPv6 route entry of ::/0. This means that 0 or no bits need to match between the destination IP address and the default route. Structure of an IPv4 routing table. IPv4 was standardized using the now obsolete classful addressing architecture. The IPv4 routing table is organized using the same classful structure. Although the lookup process no longer uses classes, the structure of the IPv4 routing table still retains it in this format. An indented entry is known as a child route. A route entry is indented if it is the subnet of a classful address, class A, B, or C network. Directly connected networks will always be indented. They're always child routes, because the local address of the interface is always entered in the routing table as a /32. The child route will include the route source and all the forwarding information, such as the next hop address. The classful network address of this subnet will be shown above the route entry, less indented, and without the source code. That route is known as a parent route. Structure of an IPv4 routing table. An indented entry is known as a child route. A route entry is indented if it is a subnet of a classful address, class A, B, or C network. Directly connected networks will always be indented, child routes, because the local address of the interface is always entered in the routing table as a /32. The child route will include the route source and all the forwarding information, such as the next hop address. The classful network address of this subnet will be shown above the route entry, less indented, and without a source code. That route is known as a parent route. The concept within the structure of an IPv6 routing table is slightly different. The concept of classful addressing was never part of IPv6, so the structure of an IPv6 routing table is very straightforward. Every IPv6 route entry is formatted and aligned the same way. Administrative distance. A route entry for a specific network address, prefix and length, can only appear once in the routing table. However, it is possible that the routing table learns about the same network address from more than one routing source, except for very specific circumstances when only one dynamic routing protocol should be implemented on a router. Each routing protocol may decide on a different path to reach the destination based on a metric of that routing protocol. This raises a few questions, such as the following. How does the router know which source to use? Which route should be installed in the routing table? Cisco iOS uses what is known as the administrative distance, the AD, to determine the route to install into the IP routing table. The administrative distance, AD, represents the trustworthiness of the route. The lower the administrative distance, the more trustworthy the route source. The table shown here lists various routing protocols and their associated administrative distances. These are the default distances that these protocols will use. So we can see that at the top, directly connected, has an administrative distance of 0. Because it is directly connected on the router, it is completely trusted. Static routes are manually entered, so again, there's a lot of trust there because you're putting the route in manually. So to distinguish it from the directly connected, which are also configured, we have an admin distance of 1. egrep, which is the external interior gateway routing protocol has a administrative distance of 5, external BGP 20, internal egrep 90, OSPF 110, ISIS 115, RIP 120, external egrep 170, internal BGP 200. You don't need to worry too much about these different routing protocols at this stage, but it is be aware of these default administrative distances, because you will then see them when these protocols are used within the routing routers. Static and dynamic routing. Static or dynamic. Static and dynamic routing are not mutually exclusive. Rather, most networks use a combination of dynamic routing protocols and static routes. Static routes are commonly used in the following scenarios: as a default route forwarding packets to a service provider, for routes outside the routing domain that are not learned by the dynamic routing protocol, when the network administrator wants to explicitly define the path for a specific network, for routing between stub networks. Static routes are useful for smaller networks with only one path to an outside network. They also provide security in a larger network for certain types of traffic, or links to other networks that need more control. Dynamic routing protocols are implemented in any type of network consisting of more than just a few routers. Dynamic routing protocols are scalable and automatically determine better routes if there is a change in the topology. Dynamic routing protocols are commonly used in the following scenarios: in networks consisting of more than just a few routers, when a change in the network topology requires the network to automatically determine another path. For scalability, as the network grows, the dynamic routing protocol automatically learns about any new networks. The table shown here below is a comparison of some of the differences between dynamic and static routing. So, feature by feature, the configuration complexity. In dynamic routing, independent of the network size. In static routing, it increases with the network size. So the more complex configurations are required, the more the network grows in static routing. In dynamic routing, it really makes no difference. Topology changes. In dynamic routing, it automatically adapts to topology changes. In static routing, the administrator intervention is required. For scalability, dynamic routing is suitable for simple to complex network topologies, whereas static routing is really only suitable for simple topologies. In terms of security, in dynamic routing, security needs to be configured, but in static routing, it's inherent. In terms of resource usage, dynamic routing uses CPU, memory, and link bandwidth, but there are no additional resources needed when applying static routes. In terms of path predictability, in dynamic routing, the route depends on topology and the routing protocol used. But in static routing, we explicitly defined by the administrator. Dynamic routing evolution. Dynamic routing protocols have been used in networks since the late 1980s. One of the first routing protocols was RIP. RIP version 1 was released in 1988. But some of the basic algorithms within the protocol were used on the Advanced Research Projects Agency Network, ARPANET, as early as 1969. As networks evolved and became more complex, new routing protocols emerged. The table below classifies the current routing protocols. Interior Gateway Routing Protocols, IGBs, are routing protocols used to exchange routing information within a routing domain, administered by a single organization. There is only one EGP, and it is BGP, Exterior Gateway Protocol. BGP, Border Gateway Protocol. BGP is used to exchange routing information between different organizations, known as autonomous systems or ASs. BGP is used by ISPs to route packets over the internet. Distance vector, link state, and path vector routing protocols refer to the type of routing algorithm used to determine best path. As we can see in the table, we basically split into two camps. So interior gateway protocols include distance vector and link state. Exterior gateway protocols include path vector. Under distance vector, for interior gateway protocols, we have RIP and eGRIP. For link state, we have OSPF and ISIS. For exterior gateway protocols, we really only have BGP. Dynamic routing protocol concepts. A routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the choice of best paths. The purpose of dynamic routing protocols includes the following: discovery of remote networks, maintaining up-to-date routing information, choosing the best path to destination networks, and the ability to find new best path if the current path is no longer available. The main components of dynamic routing protocols include the following: data structures. Routing protocols typically use tables or databases for their operations. This information is kept in RAM. Routing protocol messages. Routing protocols use various types of messages to discover neighboring routers, exchange routing information, and other tasks to learn and maintain accurate information about the network. Algorithm. An algorithm is a finite list of steps used to accomplish a task. Routing protocols use algorithms for facilitating routing information and for the best path determination. Routing protocols determine the best path or route to each network. That route is then offered to the routing table. The route will be installed in the routing table if there is not another routing source with a lower administrative distance. Best path. The best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach the network. A metric is the quantitative value used to measure the distance to a given network. The best path to the network is the path with the lowest metric. Dynamic routing protocols typically use their own rules and metrics to build and update routing tables. The following table lists common dynamic route protocols and their metrics. So for routing information protocol, RIP, the metric is hop count. Each route or router along a path adds a hop to the hop count. A maximum number of 15 hops is allowed. In Open Shortest Path First, OSPF, the metric is cost, which is based on the cumulative bandwidth from source to destination. Faster links are assigned lower costs compared to slower, higher cost links. Enhanced Interior Gateway Routing Protocol, eGRIP, it calculates a metric based on the slowest bandwidth and delay values. It could also include load and reliability into the metric calculation. Load balancing. When a router has two or more paths to a destination with equal cost metrics, then the router forwards the packets using both paths equally. This is called equal cost load balancing. The routing table contains the single destination network but has multiple exit interfaces, one for each equal cost path. The router forwards packets using the multiple exit interfaces listed in the routing table. If configured correctly, load balancing can increase the effectiveness and performance of a network. Equal cost load balancing is implemented automatically by dynamic routing protocols. It is enabled with static routes when there are multiple static routes to the same destination network using different next hop routers. Note, only eGRIP supports unequal cost load balancing. What did we learn today? The primary functions of a router are to determine the best path to forward packets based on the information in its routing table and to forward packets toward their destination. The best path in the routing table is also known as the longest match. The longest match is the route in the routing table that has the greatest number of far left matching bits when the destination IP address of the packet. Directly connected networks are networks that are configured on the active interfaces of a router. A directly connected network is added to the routing table when an interface is configured with an IP address and subnet mask, prefix length, and is active, i.e. up and up. Routers learn about remote networks in two ways: static routes and with the dynamic routing protocols. After a router determines the correct path, it can forward the packet on a directly connected network. It can forward the packet to the next hop router, or it can drop the packet. Routers support three packet forwarding mechanisms: process switching, fast switching, and the Cisco Express forwarding. There are several configuration and verification commands for routers, including show IP route, show IP interface, show IP interface brief, and show running config. A routing table contains a list of routes known networks, prefixes, and prefix lengths. The source of this information is derived from directly connected networks, static routes, and dynamic routing protocols. Every router makes its decision alone based on the information it has in its own routing table. The information in the routing table of one router does not necessarily match the routing table of another router. Routing information about a path does not provide return routing information. Routing table entries include the route source, destination network, administrative distance, metric, next hop, route timestamp, and exit interface. Static routes are manually configured and define an explicit path between two networking devices. Dynamic routing protocols can discover a network, maintain routing tables, select the best path, and automatically discover a new best path if the topology changes. The default route specifies the next hop router to use when the routing table does not contain a specific route that matches the destination IP address. A default route can be either a static route or learned automatically from a dynamic routing protocol. IPv4 routing tables still have a structure based on classful addressing represented by levels of indentation. IPv6 routing tables do not use the IPv4 routing table structure. Cisco IOS uses what is known as an administrative distance, or AD, to determine the route to install from an IP routing table. The AD value represents the trustworthiness of a route. The lower the AD, the more trustworthy the route source. Static routes are commonly used as a default route forwarding packets to a service provider. For routes outside the routing domain and not learned by the dynamic routing protocol, when the network administrator wants to explicitly define the path for a specific network or for routing between stub networks. Dynamic routing protocols are commonly used in networks consisting of more than just a few routers when a change in the network topology requires the network to automatically determine another path, and for scalability. As the network grows, the dynamic routing protocol automatically learns about any new networks. Current routing protocols include IGPs and EGPs, internal and external gateway protocols. Internal gateway protocols exchange routing information within a routing domain administered by a single organization. The only external gateway protocol is BGP, Border Gateway Protocol. BGP exchanges routing information between different organizations. BGP is used by ISPs to route packets over the internet. Distance vector, link state, and path vector routing protocols refer to the type of routing algorithm used to determine best path. The main components of dynamic routing protocols are structure, or data structures, routing protocol messages, and algorithms. The best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach the network. The best path to a network is the path with the lowest metric. When a router has two or more paths to a destination with equal cost metrics, the router forwards the packets using both paths equally. This is called equal cost load balancing.